Hello class, this is your final problem set tutorial for problem set number 5. What I did similar to last week is I took the problem set problems and changed up the wording and the numbers a little bit just so you have a parallel example to follow around uh, and what you need to do, but it's not an exact example. So here you go. So this first problem, it says here, Trump University, I hope you like that, wants to use a new tutorial to teach students about business ethics. How fitting is that? So as an experiment, the dean randomly selected 21 students and assigned them to one of 3 instructional groups. So there's 3 groups. There's a role play group that was created by the faculty, a video created also by the faculty, and a well-known course by the one and only Tony Robbins. So your task is to figure out whether or not there is a difference in how well these tutorials work. And so what you should know here about the question as it relates to specifying your hypotheses is it's not asking if one of the 3 groups was more effective than the other. It's just asking, is there any difference between the 3? So the first thing you should notice for this problem, there's 3 groups, so it's independent variable with 3 levels, and there's one dependent variable, and that's the business ethics test. So to do that, this should clue you in, okay, there's 3 groups and one dependent variable. That should tell you, I'm probably going to have to use an analysis of variance. And to do that in Excel, and this is only in Excel, you have to arrange your groups in columns. So there's 3 groups, there's 3 columns. So make note of that. And that's a hint for the final exam. So step 1 is to state your hypotheses. So the null is always going to be there as a given. It's basically saying that the 3 groups are statistically equal. There's no difference. And the alternative hypothesis is that there's some sort of difference between the means. Now, one thing you should know, they call this the analysis of variance. It's really a test of the means when it comes down to it, because that's what we're going to be looking at. The significance level, it was told to us in the problem at 0.01 level. We know that because there's 3 groups and one dependent variable, that it's going to be an analysis of variance statistics. We're going to be looking at our F-stat. And our decision rule, again, that goes back to the level of significance. So if the calculated p-value is less than 0.01, then we'll reject the null, okay? So to do this in Excel, we just go to our handy dandy data analysis toolpack under the data ribbon here. Go over to the right, the data analysis. We go find our ANOVA single factor. We click OK. And now it asks us where our data is. So we just select the 3 columns of data. It's arranged by columns, and we have labels in the first row. And then we click OK. And then when you do that, you will get output that looks like this. So what you need to pay attention to in the ANOVA output is, 1, here it gives us our 3 means, and just by looking at the 3 groups, our role play video and Robbins course, and again, this took this information right from the 3 columns, including the labels, and it gives us our 3 means. You can see that they're different, quite different. However, the next thing you need to look at is the p-value here in the ANOVA table. And it says that it is a 0.0349. This number is greater than 0.01. So what does that mean? It means the differences are not statistically significant. You're going to have to accept the null. And that is that. Now, here's the thing. We use a decision rule of 0.01 in this very specific problem. A lot of times, researchers use 0.05. More often than not, when you use 0.01, you're increasing your precision of your tests and your decision making. So if we had used 0.05 as a decision rule, we would have a different outcome. We would have to reject the null and accept the alternative hypothesis that these means and variances are statistically different. And if you have a scenario in with an F-test analysis of variance where the means are statistically significantly different, then you have to do what's called a post hoc test. And I wrote this here. And this is just for your own learning right now, okay? So those post hoc tests are typically, they have names. There's the Bonferroni procedure or the Tukey-Kramer test of mean differences. They're used interchangeably. And what those post hoc tests do is it looks at these particular means and tells and compares each one. So it compares this one to this one, this one to this one, this one to this one, and sees and tests whether or not those are statistically significant. Just to give you more precision, say, yeah, not only did the ANOVA tell us that they're statistically different, however, they're different by this much and by these particular comparisons. So that's actually helpful information to know when you get out in the real world. Question number 2. Now, this question is asking you to make a pivot table. Now, we've done this before in the past, but so just to reiterate, so this particular problem has the American Automobile Association wanted to know if there was a relationship between the type of Asian car brand and the gender of the owner. And they gathered data from 51 randomly chosen car owners. And the data looks like this. They typed it all in like this. So what you need to know is, again, Excel likes nice clean columns and rows. So you're going to reorganize this data into 2 columns, okay? You need to do that for the pivot table. So, and this is your pivot table right here. To get this pivot table, all you need to do is go up to the Insert menu at top, to the far left where it says Pivot Table, click on it. It says select the table or range, where you select everything including the column names, and click OK. And now I can put it in the existing worksheet. I can put this right here and click OK. And what you need to do, because we only have 2 variables, is in this case, since there's only 2, it doesn't matter, but you need to just pick one to be a row and pick one to be a column. So there's our table. Now we need to get our numbers, and it doesn't matter which one you grab. You need this to put that in the values box down here. And so lo and behold, you get your pivot table or cross tabulation. And that's it. So this is needed information for question number 3. So these 4 numbers here in the chi-square 2x2 template that I gave you is you just punch in your 4 numbers. So we have column 1, column 2, row 1, row 2, and you can add in the names here. So just as we had in here, or we had Hyundai and Toyota, female, male, you can take the information from the actual problem and type that in here. And then boom, it calculates everything for you. Now what you should know about the chi-square test is that it basically takes what's observed and compares it to what is calculated in terms of expected frequencies. And if you click on the cells in each of these formulas over here, because there's actually 3 calculations going on here, it does the calculations for you. There's on this website I put right here. I suggest you try it. It's a nice little calculator. It does the same thing. You specify if it's a 2x2 or 2x6 table. You punch in the numbers and it does the same thing for you. So with this test, this question is asking us if there is a relationship between the sex of the owner and the car brand. They prefer at the 0.01 significance level. This template really is helpful because it tells us our p-value and it gives us the decision rule. In this case, 0.219 obviously is greater than 0.01 or even 0.05, so it's telling us, hey, do not reject the null. Okay, they're not very different, and when I say different, that's the observed versus expected, as well as the relationship is too close between the sex of the owner and the type of car brand they prefer. Question number 4 is basically the same thing, just some things you need to be aware of. So in this particular problem, a human resources director wants to find out if there's a relationship between the day of the week and the number of times they're sick on that day. So they have the days of the week and the number of times, or the number of employees basically are absent on these days. So you're given this information. What you need to know is you can take these values here, 11, 8, 7, 14, 23, and 6, plug them in, but you need to know what the difference is from 60 because there's 60 employees. So calculate 60 minus 11, 60 minus 8, and you get these numbers here. Boom, once that's in, it does all the calculations for you. You can look at the results here in the yellow box, particularly the p-value. It's 0.002 in this particular example. It's clearly less than 0.01, so you reject the null and accept the alternative hypothesis that there is a relationship. So, and lastly, question number 5. I had to change this one up quite a bit because the original question that was given to us was quite bad. So in this particular example, the president of a pet food company would like to determine if he should be placing more money allotted in the budget next year for web-based ads of a new dog food marketed for fat and lazy dogs. He wonders if there's a strong relationship between the amount of money spent on web advertising for this new food called Doggone It and the amount of gross revenue earned. So they collected data for 20 months. And what you need to do in Excel is have your data set up, again, in nice clean columns and rows. And one little trick I like to do is I like to put in an X in what is my X variable and a Y is in what's in my Y variable. Because what you need to know about simple linear regressions, if there's only 2 variables, the actual initial calculation is the same as a correlation coefficient. And in fact, it gives you that value. However, what's different about the linear regression is you're specifying an order of the relationship. You're specifying what is an independent or X variable, and you're specifying what is a dependent or Y variable. In this particular example, what I like to do too is anytime there's some sort of figure and it's truncated, in the case of like dollars, and it says and thousands in your particular homework, is actually do the conversion yourself. So that's what I made a note here. I converted the advertising cost to thousands. So instead of 8.62, it's actually $86,000 in there. So, and keeping that simple will help you in your interpretation of the output. So just another second tip. Always have an X and a Y in your columns and make your conversions ahead of time. So to run the regression, very easy. You got your data here. You go to your data tab, data analysis, scroll down to regression, click OK, and it asks you, what is your Y data? Well, we know our Y data is right here, so you just select it and put it there, and then it asks us what is our X data, and you go in there and you select it, and we have labels. Now this problem was also asking for a scatter plot. Well, you can get that right here too with the line fit model. So if you check that box as well, click OK, what you're going to get is output that looks like this. It says summary output, and then you're going to get a plot like this. Now I put in this other line here, and I'll get to that in a second. So in the output, there's 3 things up top here you need to look at. This is that correlation, the multiple R. That is the correlation coefficient. So if you ran a correlation between those 2 columns of data using the function syntax and within the data analysis toolpack, you're going to get this same exact number. The R squared, okay, which is the coefficient of determination, is this number squared. Okay, and we'll get to that, what that means in a second. And then the standard error, which is important as well. And the next part, it also does in the ANOVA table here, because mathematically this is what you get as well. You have this significant level here, which is the overall model, and why this is important. If this was a multiple regression, meaning there was more than one independent variable, so there was an x1, an x2, an x3, you would get an overall significance of the model. However, it's not until you get down to the lower part of the table where you get into the effects of the different independent variables. So again, in this case, why it's called simple linear regression, there's only one independent variable, so we only have one variable listed here. But if there was more, they'd be listed down here. And then you would have to look individually at each of these figures. So the intercept, we need to know that figure. And this is the slope, or beta, as it's called in the regression coefficient. You need to know that. And then you need to look at the p-value for the independent variable. And again, because there is only one independent variable, this number and this number are going to be the same. Got it? So to answer the parts of the question, you just need to take information from the output. So like I said, we need to pull the intercept and the slope from the output, and the regression equation, which is this thing right here, is pretty standard. It's your predicted value is equal to your intercept, which is this number, plus your slope, or beta, times whatever X value you're selecting to plug into the equation. So in this particular case, where we know that y equals our intercept plus 46.29 times x. That's our prediction formula. So how do you interpret the slope? We have this number here. Again, remember we already did our conversions in dollars, so we know 1 for 1, and this is pretty standard how you make this interpretation. So for each $1 increase in revenue, the expected advertising cost is estimated to increase by $46.30. That's just this number here. So to predict the amount of revenue for any amount of advertising costs, in this particular example it's $87,000, you take our formula, you just write it. The equal sign, remember it's our intercept, which up here is in B4, plus, remember there's order of operations with the parentheses, the slope times, in this case, what's the value of $87,000, which is sitting in cell F16, gives us a value of $6,104,435. So, and again, this formula, whatever number you plug in, I give some other examples here, whether it's $80,000, $60,000, you can see what the predicted amount of revenue, how it changes based on that number X that you plugged in. So to interpret that correctly, all you need to be able to say is that the predicted amount of monthly doggone it revenue will be $6,104,435 when $87,000 is spent on advertising. Lastly, we have that coefficient of termination, which is the correlation coefficient. Again, that's the R squared pulled from the output here. What that number is, you can convert it to a percent, is basically saying that 34% of your dependent variable, in this case revenue, can be explained by the variation amount of money spent on web-based ads. And that's it. So it's the percent of variation in your dependent variable by your independent variable. And then your standard error, again, that's pulled directly from your output here. What does that mean? The standard error is an estimate that represents a measure of variation around the line of regression. And if we go back to our scatter plot, let me undo that move. I drew this line in here because what this intercept number here, this 2,076,724, that's the number where the prediction line crosses the y-axis. So in this particular example, when you check the box, it gives you kind of a dotted line, but if you actually drew a line to where it crosses the y-axis, that's pretty much it right there. So you can see right where that 2 million mark would be, what's going to hit right about there. So it's an extrapolation. But yeah, you don't need to do the scatter plot separately. So that's it, folks. If you have any questions, just ask.